When you're talking about electrical switches, usually this is the sort of thing that comes to mind. But if you're discussing in the context of electronics, then you may be thinking about an electromagnetic relay or a semiconductor transistor. However, what is less likely to be associated with this topic is a diode. Hello, and welcome back. Today, I want to talk about diodes and how they can be used as signal and power switches in the RF world. So, if you're curious about that and much more, then keep watching. To start things off, whenever we're talking about a switch, we're referring to a component that has two states. The on state, when current or signal can pass through, and an off state, when the current or signal is blocked. The transition between the two states being controlled by some form of action or control signal. In this case, a finger. Now, the fundamental purpose of a diode is to let current pass through one way, but not the other. This is easiest to illustrate when a sine wave is applied to one side and only half of the waveform passes through. Even though it's not that obvious, the component is working like a switch. If a direct current is applied, it turns on and lets the current pass, and if the current is trying to go the other way, then the diode turns off and blocks the current. So, it is possible to use a diode like a switch and control it using the signal that actually needs to pass through it. But is it possible to separate the control and the useful signal? As we've already seen, if you take a diode in series and apply a 0-volt centered sine wave, then only half of the waveform passes, while the other half is blocked. This is useful when you're trying to rectify, but it's quite problematic if you wish to maintain an unaffected signal. Now, if we take a sine wave that is centered around a positive voltage that is high enough to account for both the waveform's amplitude as well as the diode's forward voltage, then all of the wave will pass through. And at the same time, the reverse is also valid. If we apply a large enough negative shift, then nothing will pass through. And this is the fundamental way in which a diode can be used to switch a signal. You take an AC signal, combine it with a DC bias, and then apply the combined signal to the diode. Based on the bias value, the signal will either pass or be blocked. And commonly, you need to re-separate the two, so some sort of DC filter is needed. Based on the exact voltage polarity and amplitude combinations, as well as how the diode is placed, you have multiple responses possible. You can have the diode either in series or in parallel, and based on the direction it's pointing, it will either let the signal pass or block it. To get this behavior to work, usually you don't need any special type of diode, you just need the right amount of bias. So, to test this principle out, I prepared a few basic circuits in the simulator. I got a 20 volt peak-to-peak 50 ohm signal source of 1 MHz and a 50 ohm load. Now, just to be clear with the voltages that we'll be using, the signal source driving an open circuit provides a 20 volt peak-to-peak signal, whereas if it's driving a 50 ohm matched load, then it's only outputting a 10 volt peak-to-peak signal. Anyway, coming back to the circuits, for DC isolation, I'm using series capacitors in both circuits, and for AC isolation, I'm using inductors. For the parallel circuit, I just need a single inductor, but for the series circuit, there are two inductors to complete the DC path. Finally, as switch diodes, I use the typical 1N4148. Now, to test the operation of the circuit, I used a signal source which switches between two voltages, and in the first case, to get the diodes to switch off, so when the first diode is not conducting, then the signal applied to it will have an amplitude of about 5 volts, so half of the incoming signal, therefore the control signal needs to be at least 5 volts, whereas for the other circuit, to get it to not conduct, so therefore to block, we need to overcome the full amplitude of the incoming signal. So that's why I'm using a minus 10 volt amplitude. So with this signal, there is nothing passing through. Anyway, on the other hand, to get the diodes to conduct, we need to apply a signal of the same or preferably larger current than the RF signal. So in the first case, if we check the current coming from the signal source, as well as the current coming from our control voltage, and just to make things clear, add in the output, we can see that we are getting our circuit to block when the control signal, so IV6, is larger than the RF signal. So this is getting the diode to conduct and to block the incoming signal. For the second circuit, we are getting our diode to conduct when we apply a current, so V5, which is larger than the incoming signal, about 100 and something milliamps. So both diode-based circuits do work and are achieving the target of either switching an RF signal on or switching it off. Today's video is sponsored by GLC PCB. They provide easy, affordable, and reliable PCB and PCBA solutions, empowering electronics engineers to develop projects efficiently. For today's project, I will be using a set of boards to test out a couple diode switches. One will be a more simple single parallel switch, while the other will be a more complex series parallel double pole switch. Ordering a set of boards is as easy as dragging your Gerber files onto their website and setting a few configurations. Up to 8-layer boards can be obtained for as little as $2, and you can get a $30 coupon for the 6-layer boards. So even larger PCB sizes can be obtained for only $5. Easy to use, affordable to make, and reliable. Check out the link in the description for more details. This method of using a diode to switch a signal does indeed work. However, it has a major downside. The only way to get the signal to pass is to apply a control current larger than the peak signal current. In other words, even though you have a switch, its gain is less than unity, which is not that great. So the next thing to discuss is a particular behavior of the diode, which is typically considered a nuisance, but in this use case can become quite helpful. To highlight this, I prepared the very first circuit we looked at. So a diode in series in between a signal source and the load. And in this case, I used a rather slow diode, the 1N4004. Now, when you apply a rather slow 500 Hz signal to it, on the other side, you get the expected result. Half of the waveform passes and half doesn't. So no surprises here. Now, if we increase the frequency to 5 kHz and we look again on the output, maybe just zoom in a bit, we see a small deformation appearing. For a very short period of time, the diode is conducting the other way before suddenly switching off. Moving to an even higher frequency, so 50 kHz in this case, and zooming in again, we see that this leads to a longer period of reverse conduction. However, if we compare this to the previous waveform, the actual time in which the diode was conducting the other way was once about 4.4 microseconds, and in this case it's again 3.2 microseconds. So it's quite a similar amount of time in which the diode conducts in the reverse direction. So this is its transition time, the time it takes the diode to switch from conducting to blocking. And this specific parameter is also defined in the model, at around 4.3 microseconds. Now, of course, the exact time period is impacted by multiple factors, but importantly, it's never really zero. Anyway, coming back to our circuit, if we move to the last most extreme use case, so again I increased the frequency by factor 10, so we're now at 500 kHz. If we look on the output, and again zoom in, we see a continuation of the previous behavior. The diode is conducting the other way for a longer part of the sine wave. But the exact amount of time is now much smaller, only about 700 nanoseconds. Now, in a PN diode, you make it conduct by applying a positive bias, which pushes the charge carriers to recombine in the junction. In contrast, applying a reverse bias pulls the charges apart, preventing them from combining. The phenomenon we are seeing is what happens when you transition from one operating regime to the other. All the charges that were pushed into the junction cannot be instantly pulled apart, so even though you're applying a reverse potential, for a short period of time, you will still have current passing through. So in the case of the 500 kHz signal, all of the charges that were pushed into the junction during conduction have time to be removed, because the time available to push them in the first place is also very short. The transition time specified in the model only holds if the junction is saturated with charges, which is not the case. So even though the frequency is very high for this particular diode, it still manages to stop conducting at some point. Now, the interesting thing here is that we can easily create an imbalance. If we apply a small positive bias, say shift our 5-volt signal by 1 volt, and look again at the behavior, so we have the same signal as before, it's just shifted, but this time on the output, we fully see our incoming signal. So the diode is no longer capable of stopping conduction, since the charge carriers never fully exit the junction. Now, in contrast, if we apply the same 1 volt of shift to a lower frequency signal, so back to the 500 Hz one, so this is the incoming signal with the shift, then not much happens. We still get the same chopping behavior. Now, just to validate this behavior, I will also try out this experiment in real life. What I have here is a 1N4004 diode placed in series between two SMA connectors connected to a signal generator on one side and the oscilloscope with a 50 ohm termination on the other. If we apply a low frequency signal with zero DC bias, the diode is blocking as expected. But when we move to high frequency signals, we see the reverse conduction effect appearing, which does not keep the diode fully conducting during a sine wave period. Adding in a bit of DC offset, however, does let the signal through. But if we keep the same offset and signal amplitude, but change the frequency, we see the chopped up signal reappearing. So this is behaving just like in the simulation. If we recreate the initial setup with DC and AC blocking, and we resimulate, we can see that we are able to switch an RF signal, which is approximately 40 milliamps in amplitude, by using a DC current of only 2 milliamps. So we don't need very high levels of bias current to use the diode as a switch, we just need to keep it in the operating mode in which it doesn't have enough time to turn off. Last thing to mention about the PN diode is that while you can use it in this operating mode, usually the off state is quite problematic because of the junction capacitance. So even though the diode is not conducting in the classical sense, it still has quite a lot of capacitance, which lets some of the signal pass through. That is why the signal does not completely disappear in the off state. This behavior is present in any PN diode, but it's not really an intended characteristic, so it's usually not that well controlled. However, there is a diode in which this phenomenon is enhanced together with some other benefits. The PIN diode, a PN diode with an I in the middle. Here, the I, or intrinsic layer, slows down the charge carriers, but also allows for very low junction capacitance, giving a structure that can be controlled by slow signals, but which in turn is very good at controlling high frequency signals. If you want to try things out in the simulator, you have SPICE models for PIN diodes available, like this one from Infineon. It's not perfect since it's based on the diode model, but it's good enough for most applications, especially for small signal AC simulations. So just to test it out, I took both the series and parallel configurations and added in a control signal to see the conduction and blocking capabilities of each. So if we now simulate and first check the conducting behavior, we can see that both circuits have minimal levels of attenuation. Both are usable at almost any frequency above, say, 10 MHz. Now, if we check the blocking capabilities, so the parallel and the series circuit, then the parallel circuit seems to behave much better at high frequency. If we check, say, 440 MHz, we are getting about minus 34 decibels of attenuation. Now, one of the circuits I used in the past on the input of an SDR was a SAW filter. I used this to isolate only the 70 centimeter band. However, the SDR would be highly impacted when very strong signals appeared in the area, like when I was transmitting. So, to test out the pin diode switch, I wanted to see how it can be used to attenuate the incoming signal, to prevent the overdriving of the filter and the radio. First, I took the filter board that I had and modified it a bit to add in the diode, as well as the other necessary components. So the series inductor, a local decoupling capacitor, and then a series resistor through which the whole circuit is supplied. So the whole thing came out looking quite compact. Now, to test it out, I used the VNA and first observed the diode in the off state. So what we're getting is the transmission characteristic of the SAW filter. So no real surprises here. 2 decibels of attenuation is perfectly normal for this component. Next, when I turned on the diode, applying a control signal, the achieved attenuation was a bit smaller than expected. Instead of the 38 decibels observed in the simulator, I only got about 16 to 18 decibels, which is more than just a bit of error. So, is the simulation model wrong? Is that why the large difference is appearing? Well, actually, no. The problem lies in the fine print. You should always read that. Now, the diode model that we are using clearly states that it applies for the chip only, the silicon. And if you pay a bit of attention to the files that the manufacturer provides, you'll see that it contains a README, nobody reads the README, a package file, and the actual model that we're using. So the diode that I have comes in multiple package options, each of them having different amounts of series inductance. And for my experiments, well, I chose the BA592, which has the largest amount of series inductance. So while the silicon itself is a very good diode, the final performance that you get is impacted by the package that you're using. This is sometimes included in the model, or it's a separate file like in this case. But when it can affect results, especially when simulating high-frequency circuits, it should never be overlooked. So anyway, I took the model and included in the package to create a new subcircuit, and if we simulate both circuits to compare the behavior of the die by itself and the diode in a package, and we just look at the output attenuation results, we can see that while the diode by itself should be providing quite a lot of attenuation at 440 MHz, around 34-35, when you include the package, you're down to only about 13 decibels, which is much closer to our experiment. When it comes to pin diode switches, there are a lot of topologies out there. However, the last circuit I wanted to try out today was a single pole double throw switch that uses a single control signal. Usually, this sort of circuit is implemented using 2 separate bias signals, but I wanted to see what sort of performance you could get when a single bias signal is used. So first, I combined a set of series switches that are driven by the same incoming signal, so in the middle, and driving 2 loads on the outer edges. So to drive them, I have a single supply, which is current limited by a resistor, and then the current forward biases one diode, turning it on, but reverse biases the other one, turning it off. If we check the circuit, we can see that this is giving a relatively small amount of attenuation during conduction, but also a pretty decent amount of isolation. Anyway, to enhance the effect, I added in a second set of diodes, so both of the switches are now combination series parallel switches. The diodes are placed so that one is always conducting and one is always blocking, and the idea behind this should be that this arrangement should have a minimal effect on conduction, but it should help with the blocking. Anyway, if we check this circuit, we can look at the side which is off, compared to the previous one, see that we have a clear improvement, and if we look at the conducting side, there is a minimal impact. So the green trace is the more complex 4-diode switch. Now, the way in which you switch the switch is by either applying a positive or a negative voltage. So initially, with the positive voltage, the left side is off, while the right side is off. Whereas with the negative bias, the left side is now on, so we're getting the exact same trace, and the right side is off. Again, a nice overlap of the traces. Now, the final thing to mention about the circuit is that I also added in this extra resistor that provides a clear 0-volt DC bias when no signal is applied. So if we leave the control plane floating and we check the response, we can see that signal is attenuated from exiting either one or the other side. The design was built on a single layer, with the second layer of the board being kept as a ground plane reference. All of the components nicely flow without any bias or other tricks. The control signal is applied on the top side, the input signal on the bottom, and then the two outputs are to either side. So the signal coming in from the bottom should be going out one way or the other, depending on the polarity of the control signal. To test this out, I first connected the input side to a 60 MHz signal, and then the outputs are going to two oscilloscope channels terminated with 50 ohm terminations. Since the bias voltage is very small, the switch will only work with small amplitude signals. So for this test, I will be using a 200 mV peak-to-peak RF signal. First, if we turn on the signal source, we can see that with no control, there is no signal passing through the system, so both ports are being blocked. However, if we apply a positive voltage, then the 60 MHz signal goes to one side. And if we apply a negative voltage, then the signal appears on the other port instead of the first one. So the switch seems to be operating as it was shown in the simulation. Next, I again connected the board to the VNA to check the wideband response. So I'm measuring from 1 MHz up to 1 GHz. And here I used a single port and checked the transmission characteristics in 3 situations. First, when no bias is applied, we see about 20 decibels of attenuation. So while I did measure only one port, this should still be the case also on the other side. Then I applied a 2 volts control bias. The channel I was measuring was in conduction, so this gave a relatively low amount of attenuation, somewhere in the -3 to -7 decibels. And then, by reversing the bias, so applying -2 volts, we got quite a bit of attenuation, somewhere in the -36 to 39 dB. Now, just to see if the results are good or not, I also overlapped all 3 of them and recreated the measurement in the simulator to be able to compare the two. And well, in short, while the two graphs are similar, they are not identical. The attenuation characteristic when the switch is open seems better, but at the same time, the conduction characteristic when the switch is supposed to be conducting seems worse. So there are some deviations in between the simulation model and real life. Things like the biased inductors were not properly modeled and no transmission line losses were considered, but regardless, the switch does work, even if it needs a bit of fine-tuning. In the end, while these were not the most efficient uses of the pin diode as a switch, the principle still holds. You can use diodes to switch signals. It's quite a common practice when you need a very compact device which can be driven from a distance and is used at relatively high frequencies. Both high and low power switches are commonly built using diodes in all sorts of circuits, ranging from transceivers to signal processing circuits and even radars. And with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.